Today we'll create a cyclic symmetric prestressed modal analysis of the third stage compressor blade and disc assembly. We'll begin opening the third stage disc in its own window and entering the pre-post Simcenter 3D module. We'll create a new FEM of the disc and idealize part. We're not going to take any of the bodies yet, but when we do, we want to make sure we use high-res polygon bodies because we're going to be doing a contact analysis where we'll need to have better accuracy in the contact regions. We also want to specify a Cyclic Sys that we'll use for our cyclic symmetric boundary conditions. Alright, so we'll begin in the idealize part and we'll manage our visibility with layers. We'll get an associative copy of the disk on layer 11. We'll go ahead and hide the original component on layer 1, and we'll start to create some construction geometry on layer 12 to help us get our cyclic symmetric segment of the disk. So here we'll go ahead and take a section view of the disk, and what we'd like to do is first trim off the front and rear of the disk. So to do that, we'll need to go into the modeling application to use the trim command. And we'll trim it to a plane on the disk here. And we'll do the same thing to the aft side. Alright, next we'll create some curves that we'll use to generate a surface that we'll use to generate a cyclic symmetric slice. Now these blade slots are not perfectly axial. There's a little bit of a twist, as you can see from the section cut. So what we'll do is I'll generate some curves going from the midpoint of these two lines that we'll use for one of our edges of a ruled surface that we'll create that will be from the axial, a curve on the axis of rotation here of the disk out to that curve. Alright, so this ruled surface that we've just created isn't quite large enough to trim the disk. So let's make it a little bit larger. You can use the enlarge surface command for that. And here we can just pull on the handles enough to get it a little bit larger than the disk. Alright, so that looks good for one of the trims. We also want to trim it on the other side as well. So a quick easy way to do that is to make a copy of it. And we'll make that copy by rotating it about the axis. And we'll use a 3-point rotate by 3 points motion. So our vector will be the x-axis, that's the axis of rotation. Our pivot point will be at the origin, also along the axis of rotation. And the 2 points that we'll select will be here on the OD of the disk. So that should be the angle of one segment there. Alright, so that looks good. Before we can trim to those faces, though, we have to trim the bottom off of the disc. So let's do that next. I'll just use datum plane in the Y, and we'll reverse it. And now we can use those new faces, making sure that we use face or plane for the tool option. Alright, let's go ahead and turn off our construction geometry, and we've got our cyclic symmetric segment ready to mesh. So let's go ahead and bring that cyclic symmetric segment into our FEM, which is where we'll do our meshing. And here we want to select that body as high res as well. Polygon body resolution will be high, so that we'll, because we're going to be doing a contact analysis, and we'll use that cyclic axis as well. Alright, so that geometry is on layer 11. Make that our work layer. And we'll create a mesh on the body. We'll take a look at what the recommended element size will be, and we'll drop that at least in half, 1/10 of an inch. And we'd like to use the surface curvature based size variation to refine the mesh automatically in areas of high curvature. And we'll make sure we get 2 elements through the thickness. And we'll also use a small feature tolerance of about 10%. That will clean up some of the small edges. Alright, so we missed the 2 elements through the thickness, but that looks pretty good. You can see we've got good mesh refinement in the area of contact as well as in some of the high curvature areas. So that looks good. Let's go ahead and assign a material to the collector. We'll make this out of titanium. Alright, next we'll create a mesh on the blade. So let's go ahead and open that in window, create a FEM from that. And for this one we don't need to do any idealization, so we'll just select all bodies at high res, Nastran structural environment. And we'll go ahead and mesh it. This time we will get the 2 elements through thickness. We want to make sure we get at least 2 elements through the thickness of the blade there. Alright, and then we'll go ahead and assign material. Same titanium, and here we can name the collector if we want as well. Alright, so now we're ready to assemble those 2 components in an assembly FEM. We'll go ahead and create an assembly FEM of the compressor assembly. So this is sort of like a sub-assembly FEM. At the sub-assembly level, create a new assembly FEM. Nastran structural environment, and we are going to define a Cyclic Sys, but because we don't have one currently to select, we'll leave it blank for now and come back to it in just a moment after we've added the disk to our assembly FEM. So let's go ahead and map that stage 3 disk in there. Here we'll say list only associated models and map it to the original layers. Now we also want to map in the blade, and you can see there's 72 of them Can be a little bit tricky to find the right one because we need the right one for the right slot there. So we'll go ahead and take a guess that it'll be that one. And now let's go ahead and turn on the original layers that we used to mesh the hub, the disc, and the blade. You can see we've got the blade in the correct location there. If we didn't, we could ignore that one and pick a different one to get the right one. All right, so it looks like the mesh was on layer 222. All right, so that looks good. Let's go ahead and resolve any node and element label conflicts using the Assembly Label Manager. Here you can see we do have labeling conflicts. We can go ahead and automatically resolve those, or we could manually specify ranges that we'd like for those nodes and elements in the various components. All right, now we're ready to define our Cyclic Sys. And we can use the one that's in the stage 3 disk that we had defined earlier. We'll use that in our assembly fem, and we'll create now a sim off of our assembly fem, again using the original layer placement for the objects. We'll create a solution 401 multi-step nonlinear analysis, selecting large displacements. And we're going to create two subcases. The first is going to be a nonlinear static subcase where we're going to spin it up to 4,000 RPM. I'll go ahead and take the defaults for the end time and the number of increments. And then we'll create an additional subcase. Once it's spun up, we'll get the modes that will be prestressed based on that 4,000 RPM. And we'll go for the first 3 modes and the first 4 harmonics. We'll specify a harmonic set 0 through 3. Okay. Now we just need to specify some loads and constraints. Let's go ahead and begin with a constraint on the forward face here. We don't want that fixed though. That's going to be a little over constrained. Let's go for a user-defined constraint. Using the global cyclic axis that we had just specified, so we'll constrain it in theta and z. We'll let it grow radially. We'll go ahead and define our rotational load. Here we can specify it in whatever units we're comfortable. I'll put it 4,000 RPM. Next we'll specify our cyclic symmetric boundary conditions. And I'll use the automatic pairing algorithm, and we'll select one of the faces, and here we can preview to see that it's able to select the other cyclic face, and it's calculated 70 segments and the segment angle. And we're not going to specify any optional parameters, and we've created our cyclic symmetric boundary condition. All right, next we'll go ahead and specify our surface-to-surface contact. For this we'll use the automatic pairing algorithm. We'll search for face pairs between these two bodies at 1/10 of an inch, or 100th of an inch actually. And here you can see it's found several face pairs. We'll specify static friction coefficient, and min search distance. In case there's any initial penetration, we'll specify a negative 100 thousandths of an inch. All right, so at this point we're just about ready to solve. Let's go ahead and specify a thermal load here as well. And I have a thermal load defined in a field, which is from an axisymmetric analysis that we had done earlier. And here you can see the field is in the axisymmetric plane. And what we're going to do is map that axisymmetric temperature into a 3D model. It'll sweep those temperatures through the theta direction to map them onto those temperatures onto our 3D cyclic symmetric segment. All right, so now that we've applied that temperature load, we can go ahead and visualize how those temperatures were mapped onto our 3D body. All right, and that looks good. All right, so let's go ahead and save and solve. All right, now it looks like we have an issue. The model setup check caught a problem. Here you can see that it's saying there are labeling conflicts that we need to resolve. So when we created that cyclic axis, we did that after we did our original assembly label manager conflict resolution. We probably should have done that after we had specified that Sys. So there must be some Sys numbering conflicts. Let's go ahead and resolve those and solve. All right, while we're solving, I'm going to go ahead and pause the movie, but in the bottom right-hand corner of the solution monitor, you can see that just a little under 9 minutes has elapsed for it to solve the prestressed modal analysis. So now let's go ahead and take a look at our results. Here you can see we have results in two subcases. One is the nonlinear statics, where we spin it up to 4,000 RPM, and we can see our displacements due to it being spun up. And we can also see our contact pressures due to our surface-surface contact. Little finer mesh on there would give us a little better resolution on the pressures. That looks good though. And here you can see our first four harmonic indices for our modal results. It's a little bit difficult to visualize what's going on modally with just one cyclic symmetric segment, looking at a Fourier cyclic modal analysis. Let's go ahead and display all of the cyclic symmetric segments, and here you can see for harmonic index 0 our mode shape for the full wheel. All right, so there's harmonic index 0. You can look at harmonic index 1. And then as we move up in harmonic indices, we can see the various changes to the mode shapes. And there's harmonic index 3. It takes a little bit to generate an animated mode shape, but we have a couple of different options in creating mode animation. We can either do just a standard modal or forward or backward wave, looking at the whirling modes. So here I have a movie of, I think it's harmonic index 5 as a standard modal and whirling forward whirl. Alright, so that looks good. Next, let's go ahead and make a change to the blade root radius. Here it's looking a little bit small. Let's see what kind of an effect making a larger radius here would have on the stress on the blade. So it's very quick and easy to do this evaluation and make this change. Here you can see the geometry is updated in the finite element model. The update button is pending. We'll go ahead and update the mesh. There you can see now the mesh conforms to the larger root radius for the blade. We'll go to the assembly fem. You can see that larger root radius is reflected. We'll go ahead and resolve any label conflicts due to the update to the mesh. And so that we can view the results side by side, we'll go ahead and clone the original solution, and we'll call the cloned one S2. And also, so that this will solve a little bit faster, I'm going to remove the cyclic modal analysis since we're just looking for the stress due to the 4,000 RPM rotational load. And I'll go ahead and pause the video. Here you can see it solves in just a little over 3 minutes, 3.5 minutes, instead of closer to 9 with the cyclic modal. So let's go ahead and look at our results side by side. I'll go ahead and open a 2-view layout, and we'll put our original VM stress results on the left with our smaller blade root radius, and then with our larger blade root radius we'll put that on the right, and we'll go ahead and synchronize the views. That will allow us to be able to zoom and pan both of them at the same time. Here we'll go ahead and take a look just at the stresses in the blade. So I'll go ahead and turn off the disk components. And here you can see the change in stress on the blade root. Just so we can see this maybe a little bit better, let's go ahead and do an average stress plot. These stresses are unaveraged. Let's go ahead and average those. And also you can see the legends are a little bit different so that we can get a better view of the difference in the stress. Let's go ahead and specify the same min and max for each of the results. So here we'll go up to a max of 4780 for both. Alright, so there you can see the larger radius has reduced the max stress in the blade. And that concludes the demonstration.